Okay, as I said before, what we're going to do today is look at a toy car machine learning example. What we're going to do for this is basically predict how a toy car moves using an algorithm. So this is the toy car that my son has. He's had it for 20 years. He's quite grown up. And what we're going to do is we're going to measure how long it takes to travel on certain distances. And using those measurements and a machine learning algorithm, the program that we're going to look at in a minute, we're going to predict it for a brand new value. So let's see it in action. So here it is, just outside of our house. We've measured 1, 2, 3, 4, 5 marks on the ground that each represent a 1 meter point. We've set it off. We've had my wife's helped me with the stopwatch, and we've recorded when it's past 1 meter, 2 meters, 4 meters, and 5. What we've then done is we've used this data to create a model of how to predict how long it will take to travel 3 meters. As you remember, we haven't measured 3 meters up to this point. So here it is in Excel, good old Excel. Now, as a human being, you'll look at that, and in your mind's eye, you're going to draw a kind of line here. And at 3 meters, it's probably going to be about halfway through there. And this is pretty much exactly what a machine learning, what this particular machine learning algorithm will do. It will take the data, it will average it together, and it will create a line as a rule of thumb that it will follow for all these data points. Now, what's interesting about that is it's going to derive this only based on the data. It doesn't need to know things like, because you'll go, well, there's a way of solving this. We create a program or a spreadsheet that works out that we can work out what the speed is, and then given a distance, if we know the speed, we can work out the time it takes. And that's traditional programming. That's using a set of knowledge. So you've got a set of equations, and you'll build some program to model that equation. But for this, the machine learning algorithm doesn't need to know concepts like distance and time. All it needs to do is know data, and what it will do is it'll work out purely from the data and its data analysis that there should be a line going through there, and it should be somewhere in the middle. Let's have a look at the example. So here's the computer program I've created to model the toy car movement. I'm using Python here because quite a lot of the best machine learning libraries are available in Python. For this whole presentation, I'll be using something called sklearn as my machine learning library. Here I'm creating an input and an output array, and in that input array, I'm basically putting the distance. The second part of this array you don't need to worry about at the minute, and I'm setting the output as the output array the time it took. So we've got data here for 1 second. 6.5 seconds, 2 seconds, 12.38, 4 seconds, and 5 seconds. And then I'm taking that data and I'm fitting it into this section, which is the really key part. That's where I'm taking that data. I'm using the linear regression model. You can see that we're following roughly a line there. I'm asking the library to fit against that data, and basically put it all together. Right at the end, and then of course I'm printing my prediction time for how long I think it's going to take to do for 3 seconds. So let's just do that right now, and we'll worry about it right at the end in a minute. So run the toy truck scenario. It runs. It takes a few seconds. There we go. The predicted time to travel 3 seconds is 18.36 seconds, and that seems quite reasonable. In actual fact, I said that we recorded it for 1, 2, 4, and 5 seconds, but to know if this model is any good or not, we really needed to have actually measured for 3 seconds as well. And if you look up here, that I've put that data for 3 seconds and I've hashed it out. So the data I get, we actually got was 18.68 seconds, and our machine learning model reckons it was 18.36, and that's close enough. So right at the bottom, I have put within a tolerance of about plus or minus half a second. That's what we expect the time to be. Of course, there's slightly screwy things we can try and make the model predict, and that's what I've just hashed out now. We've got data there from 1 second to 5 seconds, and we basically kept part of that data to one side so that we could perform that validation on it. What if we give it a nonsense number? Testers always know how to use nonsense numbers. What if we ask it to predict minus 3 seconds? Just makes minus 3 meters. Sorry, that should make no seconds. No sense. It should produce a negative number, and you can't have negative time. Negative time isn't a thing. What if we try and use 300 meters? What's special about 300 meters? Well, nothing really, but we collected data from 1 to 5 meters. 300 meters is way outside of that range, and yes, there should be a line there, but we are going well beyond the bounds of what we had data for. That should, in your brain, that should ring alarm bells, and you should say things like, surely it might run out of battery on such a long haul. So if we run that, here we go, minus 3 meters. Yes, it gives us a negative number. It will give us a number for 300 meters. And this just shows that what we've produced here is we've produced something that gives us numbers, but we have to be very careful, which is good testing, about how we use that model, and we can make it stretch beyond the bounds of the data that we've originally provided it with, and that's a bad thing. It's something to be very mindful of, and of course testers are very good at being mindful and championing this kind of thing. Okay, this kind of example of machine learning where we create a model that allows us to predict a numerical value is called regression. There's obviously going to be another type of machine learning later on, but we'll worry about that when we get there. What we're now going to look at is something called dimensionality. And it's often called the curse of dimensionality, and we'll find out why in a minute. Back in the 90s, when I first worked on an AI system, there was this mentality that all you need to do with machine learning was just throw all the data in there and it would work things out. And the modern renaissance that we're having, you're seeing very similar things. It's like, just throw that data in there and that machine learning will nom on it all, it'll eat it all, and it'll create wonders out of you. Tends to be a fine thing. Okay, so we came up with a reasonable machine learning there. We measured 5 distance. We took 4 to use to predict the 5th, and that 5th gave us a reasonable confidence in what we'd built. But whilst there was more going on with our toy car than just put it on the ground, send it through these 5 different distances. So far, the only thing we're saying varies is, the bigger the distance, the longer it will take, and we can calculate that. Well, this particular toy car of my son comes with two power modes. There's on, which is the normal power mode, and then there's power mode, which is the grunty, fast, turbocharged mode. So let's just take a look at the difference between those. On the left, we have normal mode, and on the right, power mode. And just watch that steaming ahead. You'll also notice there'll be a bit of error because I don't drive particularly straight. So there's two power modes going on there. So that variance of two different types of things. What if I tells you that as well as just the power mode, there are 10 different types of load we could put in there? It is a dumper truck after all. And the more load we put in there, the slower it will go. And we're not always going to be driving it on the flat as well. And there are 10 different types of slope that it might have to contend with. We were just using concrete there, but turns out there's 10 different types of surface it might have to go on. And different batteries have different powers, which will mean different speed. Wouldn't you know, there's 10 different types of battery. We might not always be going straight. We might need to turn. In fact, in that little video, you'll notice when we turn, it does slow a little bit. There's 5 different types of turn we have to combat as well. All these seem really quite reasonable things, but if you take those 5 distances and those 2 types of power settings and those 10 types of load and those 10 types of slope and those 10 types of surface and those 10 types of battery, those 5 types of turn, all together to achieve something that's going to cover all that data, we need to collect not 5 types of data points, but 500,000. That's like 500,000 data points. And this is called the curse of dimensionality. Every time that we say there's a new data thing that we have to, a new type of measurement or something that we need to monitor as well, we're introducing another dimension. And that basically has the effect of growing the data that we need exponentially. And often, like I say, we call this the curse of dimensionality. The more things that we're trying to monitor, the more data that we need. And the more distributed we need that data in order to produce a good machine learning model. The second type of curse of machine learning is something called overfitting. As you could see in the video before, our experiment had several sources of error in the data. One of which was the human reaction speed with a stopwatch. That's always going to be, cause us, whatever time that we record to not be perfect. The surface wasn't even, and as you noticed, I had to sometimes steer to keep it kind of straight. Again, had to steer a little bit to keep it straight. Now, machine learning can sometimes overthink things. It can look at data points and it can try and fit them a little bit too well. We know from a data set like that, it's probably a line that it needs to follow. But every so often, a machine learning algorithm will overtune itself. Just like this. And that's and it does that from its training data. And that's why you have to be very, very cautious about trying to get too close to your training data. That's why you squirrel away some data to the side so that you can try an object that's a piece of data that's maybe here or particularly here to see, is it following this line, or is it going on some wacky path through these data points?
God, it's full of data. Wait a second. Isn't this just black box testing?
As we've spoken about, one of the huge problems with machine learning is once it's happened, it's hard to see what's going on inside. You have to treat it a bit like a black box and put examples through it and see how well it behaves. Of course, testers are brilliant at treating things like black boxes. So let's look at how you tackle overfitting. As I said before, this is why I took 5 observations and squirreled one away. I put those 4 pieces of data in through the machine learning algorithm, and we kept this item, the third item, and we used it as a measure of quality against the power of the machine learning to produce a prediction. It's important really to think about this. There's a temptation to throw all the data you have through the machine learning system so that in theory it gets as good as it can be. But a machine learning system always does really, really well against the data you train it against. What you need to do is you need to keep back a little bit of data and use it as a kind of a way of testing the quality of the machine learning algorithm to look for overfitting. See, testers are useful in a machine learning world. Next, we're going to look at the topic of bias in machine learning. It's really important. Because I can't help myself, let's look first at how we think we should fear AI systems. And then I'll show you a video about how we should actually be worried about how we use AI systems.
Hello there. Do we have a Sarah Connor here? Sarah Connor? I'm awfully sorry about this. Your screams will be recorded for training purposes.
It's important to the company to pay people fairly, and too often bias can get in the way. In future, we're going to use an AI system to determine an employee salary based on their years of experience.
Hey, I just had my salary review.
I know, the system's working really well, isn't it?
No. I have 5 years of experience, same as G.I. Joe over there. I've been put on 80,000, but he's on 100.
Well, maybe he just works harder than you.
Joe isn't the smartest tool in the shed. He does work hard, but he can barely tie his shoes.
True, and he does keep getting my name wrong. You're Gandalf. But the system's supposed to be impartial.
Well, the data you gave the system was a little all over the place, but the AI did notice one pattern. Yeah, men make about 20% more than women doing the same job. The AI didn't know better, so saw it as a rule it needed to enforce.
Oh, bugger. I like to think of machine learning as a mirror. And sometimes that mirror can make us look a little bit unflattering. It's a bit like having a child. You can say as many times to as many people, please and thank you. But it's the time that you call someone who cuts you up on the road a dickhead, that child will start repeating everything that you say. When we give information to AIs or machine learnings, often it will reproduce our decisions, and sometimes, as I said, those decisions aren't flattering. In the machine learning example we just saw, we took some examples of different types of salary, different types of experience, and different types of salary. What we didn't really know was that underneath that, there was a gulf between male pay and female pay, with females always being on less. When we gave the machine learning program this data, rather than seeing the gulf between male and female pay as something that needed to be addressed, it saw it as something that was the norm, that needed to be enforced. And so when we chose Barbara to have a pay review, she always got less than G.I. Joe. And that's one of the problems with the machine learning. As I said before, it's a black box. We can't question it. We can only try different examples to see what's up with it. And sometimes we're unaware of that bias until we see it as a pattern. America's feeling something very similar to this with its risk profile of criminals. It should, in theory, mean that whether you're black or white, you get similar sentences, but there's a bias seeping into the system. One of those examples has been a recent person called Eric L. Loomis, who has been found to be a high risk, but he doesn't know why he's a high risk, and on paper he shouldn't be a high risk, so they just locked him away. But he can't. There's nothing there to actually challenge that decision on, and that's going to be the more we use machine learning, and the more the decision making is hidden from us, the harder that's going to be to challenge. So here's our salary calculator example. Once again, I'm using sklearn, as I will do for all the exercises here, and using an input and output array. The input array, the first dimension is the user experience. The second is gender. So if someone is male, if female, there's 0, male, it's 1. Finally, for the output, it's the salary. So we feed all this information. We create this multi-dimensional array, and we again get it ready to be consumed. And what I'm going to do for this example is I'm using several different algorithms for doing my machine learning. So I'm using here the linear regression model. Here I'm using what's called a Bayesian ridge model. And finally I'm using a lasso model. I'm not really going to get into too much detail about the algorithms themselves. That's because I can only cover so much material in this presentation. But I encourage you to do a read-up of this. The important thing to understand is there is not a single machine learning model that's in use. With an example like this, you'll often create the data, get it ready to be consumed, and work out which model seems to be most suitable for the data. So we're going to run this now. And using a linear regression model, you can see it's telling me that it'll pay a man with 5 years experience 98,000, but it'll pay a woman with 5 years experience, the same level of experience, 80,000. So it's enforcing that gender divide, and it mars up with the example we had in the video. Using a Bayesian ridge, you can see it gives us, whereas with the linear regression it gives 98.7 thousand for a man. This is giving more 98.6. It's slightly different because the model works slightly different. And likewise for the Lasso model, the numbers are again different. That's, as I've said, different algorithms will produce slightly different results, and you'll see that a little bit more with the classification example we're going to look at next.